Let's now use Ampere's law to investigate the magnetic field produced by a coil of wire carrying a current. A tightly wrapped coil of wire is sometimes called a solenoid. Here's an example of one here. Tightly wrapped wire spiraling around from one end to the other. It's hollow in the middle, has a chamber, and if we run current through it, the current sort of loops around and around and around, and it's going to be generating magnetic field inside and out. So let's have a look at those fields. If we consider just a single loop of current, just I coming out of the page here, then into the page there, so current just running around in a single loop, we've seen before that it produces this shaped magnetic field in the region around it. This is that characteristic dipole magnetic field. This side on the right, where the field lines are emerging from the loop of wire, would be considered the north pole of our magnet here, and this is the south pole over here. Field lines emerge from the north and then go back in at the south. Okay, so we've got an electromagnet here, a magnetic field generated by a loop of current, north and south poles. If we put several of these loops next to each other, so if we have kind of a coil like this, which could be represented here as kind of like 3 of these loops in a row, current comes out and in, out and in, out and in, then we're going to be producing magnetic, each one of these little loops is going to be producing magnetic field. Let's sort of see what the sum of them looks like. So this particular little cross section of current through the wire with current coming out of the page right there, grab it with our hand, thumb in the direction of the current, and our fingers curl in the direction of the magnetic field that this little particular piece of wire is generating. So we see that it would be generating loops of magnetic field like that. And so would each of these 3 neighbors. Down here below, where the wire goes into the page, current's being carried into the page, grab that wire with your right hand, thumb in the direction of the current, and fingers curling clockwise. So these little sections of wire here carrying current into the page would be generating B field loops circulating clockwise. Okay, so there's kind of like one field line for each, and I want to look at these regions where they are going to be overlapping. So here, in between these two, we've got B field up and B field down. It looks like we're going to get cancellation in between here. Likewise, down here at current down, sorry, B field down and B field up, we get cancellation in the spaces in between. But say here, B field is to the right, B field is to the right, B field to the right. All of these B fields will be kind of reinforcing each other. Likewise down here, B field to the right, to the right, to the right. It appears as though all the top row cross sections and all the bottom row cross sections, they're all producing magnetic field to the right in the hollow space inside the coil. We're going to get a net field to the right in there. On the outside, sort of above the top row, we're getting B field to the left, to the left, to the left. So we should get net B field left above, and down here, B field left, 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 below the bottom row. So B field to the left below. So if we imagine adding up those magnetic field lines to produce a net magnetic field, we might get something that looks kind of like this. B field line sort of wrapping around all of those, circulating counterclockwise. And down here below, something like that, circulating clockwise. This would be our net B field. And if we imagined adding in some more field lines, we might get something like this. A couple more field lines there, coming in, going out. This line here looping all the way around. This line down here looping all the way around, like that. So we're seeing kind of a concentration of magnetic field in the space inside our coil, and a weaker magnetic field on the outside where these field lines are widely spaced. Okay, so if we extend this idea to its logical conclusion, the case of the ideal solenoid, something more like this, where instead of three kind of loose wrappings of wire, if instead we have a very long coil that is tightly wrapped all the way through with a length here that is much, much greater than the radius of its cross section. In that case, we're approaching what we call the ideal solenoid. And the extension of this picture to the idealized case will be to the effect of straightening out these B field lines on the inside and really spreading out these B field lines on the outside, minimizing the fringing that we get near the edges on the left and right. Oh, quick comparison between this diagram and this one. We are getting something like a magnetic dipole field here as well. This dipole geometry is replicated here in the solenoid case. So at the right end of the solenoid, where we've got our B field lines emerging, this is effectively like the north pole of the electromagnet that we've generated, and this side is like our south pole of our electromagnet. So extending that picture to our infinitely long solenoid, the ideal case, gets us something a bit like this. Here we have a long coil with tightly wrapped, so we have closely spaced wires. These are cross sections of the top parts of the wires carrying current out of the page, out, like this little row of what always looks like frog eggs to me. And then here below we've got a cross section through the bottom parts of the coil carrying current into the page. And we get this nice kind of uniform looking B field inside, but I want to use Ampere's law to investigate whether the B field in here really is uniform or if it depends on distance, and also what's the B field like outside our long infinite ideal solenoid, infinitely long ideal solenoid. As before, we do have fringing effects towards the ends. If our coil is not truly infinite, we will eventually get some fringing out here. And this side where the lines are emerging, that is the north pole. This down here is our south pole. Okay, let's apply Ampere's law to investigate the B field inside our solenoid. So we're going to need some kind of Amperian loop, a path, a closed path that we can draw, and a path that takes advantage of the symmetry that's present. With our infinitely long solenoid here, we don't have the kind of circular symmetry that we had when looking at just the cross-section of a single wire. Instead, we could draw a rectangular loop, say like this, enclosing a few turns of wire. We call each of these loops of wire a turn, another turn, another turn. So this very long solenoid has many, many turns in it. We could count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. 29 turns in this solenoid that I've drawn. Let's make a note of that. N equals 29 turns for this case. We'll come back to that value, capital N, the number of turns in, we'll come back to that later. Okay, so I've enclosed 3 turns of wire here in this rectangular Amperian loop. So I've got an imaginary path here, and if I've got current coming out of the page, then by right-hand rule I'm going to choose to go counterclockwise around that loop, so imagining hiking in this direction along that path. Okay, let's apply Ampere's law to that loop. State Ampere's law down here. We integrate B dot ds all along the four sides of that path. We get mu naught times the current enclosed by that path. Now, if the current running through this coil is I, then each of these three turns of wire is carrying current I out of the page. So that's current I out through our Amperian loop, current I out, and current I out. So that's 3 times current I being carried out through our loop, penetrating through the open surface bounded by our rectangular loop. So let's call this current enclosed 3 times the current running through this whole coil of wire. Okay, let's number these corners starting here at 1 to 2 to 3 to 4, and break down this closed line integral into a sum of 4 open line integrals. The integral of B dot ds from 1 to 2 plus that integral from 2 to 3 plus the open line integral of B dot ds from 3 to 4 plus the open line integral of B dot ds from 4 back to 1. That's our left-hand side expanded, and that is mu naught times the current enclosed, which is 3 times the current running through our coil, since again we're enclosing 3 turns of wire. I want to note that from the symmetry here, if our coil truly is infinitely long, and the more, then our magnetic field lines should be running perfectly horizontal. We only get fringing when our solenoid has a finite length to it. If it ends somewhere, that's where we get fringing. But right here in the middle section, we're very far from the ends. We're most near the infinite solenoid approximation, and we're getting very horizontal B-field lines from the symmetry. And the same should apply outside the coil, up here above and down here below. In the limit that our solenoid is infinitely long, then these sort of B-field lines looping around and returning back this way, they should be very nearly horizontal, and in fact perfectly horizontal in the limit that our coil is indeed infinitely long. So my point there is that along these sections, 2 to 3 and 4 to 1 of our Amperian loop, we have ds vectors parallel to the path, but in all those points our B field should be coming in horizontal there, and even down here our B field horizontal, so at a right angle to ds. So our B's and ds's are at right angles to each other along those two legs, in the limit that our solenoid is infinitely long. Hence, B dot ds should be 0 from 2 to 3 and from 4 to 1 in our ideal solenoid limit. Okay, so we're only really concerned about B dot ds from 1 to 2 and from 3 to 4. I think that I'd like to compare this Amperian loop to another nearby one. So let's draw another rectangle, and then by comparing the two, we'll be able to reach the conclusion that we want. Let's say this other Amperian loop will be also enclosing 3 turns, and the top part will be the same distance above the wire as this one is, but the bottom part will be somewhere else inside the solenoid. Okay, so comparing those two loops, we see that the integral of B dot ds from 3 to 4 here should be the same as the integral here. So those two terms should be the same for both of our loops. So that would be this term here the same for both loops. I also note that I'm enclosing the same amount of current. I enclosed is 3I in both cases, so that's the same for both loops. Turning our attention to this term, the 1 to 2 term, that must therefore be the same for both loops also. Since in our equation, this is the same for both, that's the same for both, this must be the same for both as well. And since the length here is the same for both, what I'm arguing is that the magnetic field B along this segment here must be the same as the magnetic field B along that segment there. We're proving with this Amperian argument that the magnetic field B is truly uniform inside our coil. B does not get stronger towards the middle or weaker towards the middle. B is exactly the same value everywhere inside, which we've proved by using these two loops and varying the position of the lower end of the loop from here to here. So this must also be the same for both loops. Therefore, B is uniform inside our coil. An extremely valuable conclusion, and one that makes our coil similar in its function in this new magnetic universe to that of the parallel plate capacitor in our previous universe of electric fields. The parallel plate capacitor was the thing that produced a uniform electric field. Now we're seeing that our solenoid is the device that can produce a uniform magnetic field. Okay, that's on the inside. Let's take a quick look on the outside in the space above and below our ideal solenoid. So we can consider this loop here. That'll do. How about nearby another rectangular Amperian loop with the same width, so enclosing a current 3I, but a different location for the top part. Imagine hiking around that loop. Okay, I think we can apply this same expression of Ampere's law here for our hike from points 1 to 2 to 3 to 4. Okay, this time we see that the bottom two legs are identical to each other. So that means that term is the same for both of these hikes. And we know the sides contribute nothing to B dot ds, since B and ds are at right angles through the sides. So we're left with concluding that these top segments, this 3 to 4 and this 3 to 4, that term must therefore be the same for both loops. And since this length here is the same as that length there, what we're forced to conclude is that the magnetic field here is the same as the magnetic field here. But those are different distances from our coil. So we're finding that in the ideal limit, the magnetic field outside the coil is independent of your distance from the coil. We must also, therefore, have a uniform B field on the outside as well as on the inside. What we've just concluded is that B is uniform outside our coil, as long as we're in this ideal limit. Outside our ideal coil, inside our ideal coil. Okay, but we can go even further. If the B field is the same everywhere outside the coil, then, well, what value does it have? Take a look at these magnetic field lines exiting over here. I've got, looks like 8 field lines coming out, and then they're curling around and spreading and returning, coming all the way back. Now, these 8 field lines are kind of spread across this cross-sectional area of our coil here. So they've got this much area to penetrate through, sort of the mouth of our coil here. But on return, these lines have all of infinity to spread out through. These lines have infinite space to spread way out through and come back around again. And we know the spacing between lines indicates the strength of the field. Closely spaced lines in here, strong magnetic field. But these lines have all of infinity to spread out through, so the spacing between them can potentially be huge. They could be infinitely far apart. And if the lines out here can be infinitely far apart, and we've shown that the strength of the magnetic field out here is the same everywhere, then we're forced into the conclusion that the magnetic field outside in our ideal limit must actually be 0. Because if they can be infinitely far apart anywhere, then they're infinitely far apart everywhere. If you followed the argument, and you may want to think it through a few more times yourself, what we're concluding is that B equals 0 everywhere outside our ideal coil, which is also quite like the case for our capacitor. Quick reminder on our parallel plate capacitor, the ideal capacitor that had big plates, closely spaced, with separation W that was much less than our length L, W much less than L for our ideal case. In this ideal parallel plate capacitor, it was producing a nice uniform E field on the inside, uniform E, but above and below 0 E field. We got perfect cancellation from the symmetry in the ideal limit. That's what we're getting here for our solenoid. Uniform B field on the inside, 0 B field everywhere on the outside. Oh, okay. Another kind of recap here. If you've noticed some interesting phenomena here, we've seen that a straight wire thus far produces, a straight wire carrying a current produces B field lines that loop around it like this. Straight current produces looping B field lines. But now if our current is looping, if our current is spiraling around through our coil, if we have a looping current, that produces a straight magnetic field on the inside. So an interesting kind of reversal of geometries for these two cases. And one last note for this video. We have yet another application of right-hand rule for solenoids. If you take your right hand, and allow your fingertips to curl in the direction of the current that's spiraling through our solenoid, like here, current's coming out and in, out and in, out and in. If your fingertips curl in the direction of the spiraling current, then your thumb will point in the direction of the B field that that solenoid is creating. Just like in reverse here, if the current is spiraling this way through the coil instead, curl your fingertips in the direction of that spiraling current, and your thumb indicates the direction of the B field. So here we've got a right-hand rule helping us identify the north and south ends of a solenoid that's functioning as an electromagnet.